Alright, rhythmic functions. And it's kind of a banner day because we're learning a really important one, like right now, and that's the derivative of the natural log of x. So to give you guys an idea, a feel, if you will, for what that derivative just might be, I have right here in Calc in Motion the graph of the natural log of x. So you guys can all see that in blue. And of course, at any old x value, we've put a point P and we've graphed the tangent to that point on the curve, which is the instantaneous rate of change. The slope of that tangent, which is in green, is of course the derivative. So just to get an idea of what is going on here, you can see that as the x value gets further and further away from 0, what's happening to the value of the derivative? Yes, it is decreasing. Well done. Okay, and as x gets closer and closer and closer to 0, the value of of the derivative is definitely increasing. Okay, so we want to try to come up with an actual derivative for natural log of x. So let's just look at some key values. When x is equal to 1, let's try to get it as close as we can. What's the value of the derivative? It's 1. Okay, when x is equal to 2, what's the value for the derivative? Oh, that's about as close as I can get. It is 0.5, 1/2. Interesting. When x is equal to 3, want to take a guess? Yep, you get 0.33, so that's pretty close to 1/3. You on to me here? What do you think it's going to be at 4? That's right, if you hopefully guessed it correctly, and that would be 0.25, also known as 1/4. So see if you can think of what you could imagine the derivative function to be for the natural log of x. And then let's see what happens as x gets closer and closer and closer to 0. We said before the value of the derivative gets bigger and bigger and bigger, but how big are we talking? Notice the value of the derivative here is about 4. I'm going to get closer to 0. All of a sudden it is 11, 13. I'm going to get as close as I can. 23, 27, 34. Oh my gosh, did you see that? Holy cow, it's 138. That's mighty big for slope, right? And then all of a sudden when I get to just about 0, there it is. Did you see it for just a second? It said infinity. So see if you guys can figure out what the derivative function is for the natural log of x. And write it down real quick. Go. Okay, so it looks like, based on what we noticed on the graph, that the derivative, really? My pen's not working. Hang on. The derivative of the natural log of x just seems to be 1 over x. And that is, in fact, the case. And we're going to put a big star by that because you're going to use that fact over and over and over and over again. So the general rule, of course, is you don't always just take the natural log of x. Sometimes you need to take the natural log of another function. So the derivative would be 1 over that function times the derivative of that function. Oh yeah, what was the name of that rule again? Oh yeah, that's chain. So you'll need to use the chain rule if you're doing the natural log of something other than just plain old x. Okay, so what if you don't have a natural log, if you just have a regular log? Before I launch into that rule, I just want to remind you guys of the change of base formula, which says that log base a of x, if you use change of base formula, is equivalent to the natural log of x over the natural log of a. So the way I always remember this, since you write log, the base is always down a little lower than x. I just kind of remember it like, and then this is horrible math, but this is how I remember it. The x is on top of the a, and then you put a log on the top and the bottom. So it turns into the natural log of x over the natural log of a. That's how I remember change of base formula. Anyways, let's erase that so no crazy mathematicians get angry with me. Okay, so what happens if you have the derivative, or you want to find the derivative of the log base a of any function at all? The derivative rule is this. The rule is it's 1 over u, the function itself, times the natural log of the base, a, and then times, if you need, chain rule, or times, you use the chain rule. So you times the derivative of u with respect to x. So one thing that's actually interesting / good to notice is that these are actually the same exact rule, right? When you take the derivative of the natural log of u, what's the base of the natural log? Oh yeah, it's base e. We just don't bother to write it. So using this same rule, we would get 1 over u times the natural log of the base, which is e, and then times du dx. But what's the natural log of e? Oh yeah, that's just 1. So we don't need to write that. We just get 1 over u times du dx. So really it's only one rule. Okay, so anytime you want to take the derivative of log base a of u, it's 1 over u, and then times, in the denominator, the natural log of the base. Alright, so let's practice these rules on a couple of problems. The natural log of x, oh, easy squeezy, come on, we know this one now, it's just 1 over x. What if you have the natural log of 4? That's interesting, what do you think it is? 1 over 4? Wrong. What, Mrs. Kelly, why? Guys, 4 is just a constant. So if I take the natural log of a constant, this whole thing is just a constant. So when I find the derivative of a constant, what do I get? 0. Oh, tricky. That's right. You've got to think a little bit. Sorry, guys. Right. What if we had the natural log of a function? Oh, this is a composite, right? We have a function inside of a function. So we know that the derivative of natural log is 1 over blah. The blah being 4x plus 1 times the derivative of that blah. What's the derivative of 4x plus 1? It's 4. So we get 4 over 4x plus 1. Alright, maybe you guys try the next two by yourself and then come back. Press pause. Pause me. It's okay. Alright, so hopefully you're back. Either that or you're a total cheater and you're just going to make me do all the work. So let's do the natural log derivative of the natural log of 6x squared minus 4x. So we're definitely going to need a chain rule because it's a composite function. The derivative of natural log is 1 over blah, what I'm taking the natural log of, which is 6x squared minus 4x, times, here it goes, chain rule, the derivative of that blah, which would be 12x minus 4. So that looks like something that we could probably simplify. That would give us 12x minus 4 over 6x squared minus 4x. We'll do a little bit of factoring. We could factor a 4 out of the top and get 3x minus 1. We can factor a 2x out of the bottom, and we're left with 3x minus 2, it looks like. And then what can we simplify? The 4 and the 2 can go like so. So we would be left with, let me write it up here, 2 times the quantity 3x minus 1 all over x times the quantity 3x minus 2, if we wanted to simplify. Alright, let's do the next one. This one's fun. Why is this one so fun? Because it's the natural log of x times, yep, there it is, that annoying voice again, square root of x plus 1. So, this is beautiful. Definitely a composite function. We have the natural log of a function, and that function itself is a product of two other functions. So we're going to need to do product rule and chain rule. So it starts off, finding the derivative, starts off fairly straightforward. The derivative of natural log is 1 over whatever I'm taking the natural log of. But here it comes, times the derivative of what I'm taking the natural log of. So here's where I need to use big F. So we're going to do f prime g plus g prime f. We're going to get it all set up, all the parentheses, like so. Alright, and now we just have to do the work. What's the derivative of f? 1. What is g? Square root of x plus 1. Oh yeah, and before I even try to do g prime, let's just rewrite g. G is x plus 1 to the 1/2 power. That's what g is. So I go to take the derivative of that. So that's a composite function, so I'm going to have to take 1/2 and then blah to the negative 1/2 power times the derivative of that blah. Oh, lucky for us, that's just 1. Okay, f is x. And so now, oh my goodness, I've got to simplify all of this. What do we have here? We have 1 over x times the square root of x plus 1 times, simplifying all this, we get square root of x plus 1 plus, we have half times 1 times x. So that's going to leave us with a fraction. X will be in the top, 2 will be in the bottom, and square root of x plus 1 will also be in the bottom. So now I actually need to distribute and hopefully simplify. When I multiply this, right here, do you guys see that the root x plus 1 and the root x plus 1 are actually going to cancel? Nice. So that simplifies down to just 1 over x. Alright, coming over to the next one, we're going to have, x on the top, and an x on the bottom. Do you guys see those x's are actually going to cancel? So we're still going to be left with that 1/2, And then, oh, on the bottom I'm going to get root x plus 1 times root x plus 1. So I'll even write that out. Root x plus 1 times root x plus 1 is root x plus 1 squared. So that's going to give me 1 over x plus 1 over, well, squaring and square rooting, those just cancel. And then I'll need to distribute my 2. So I'll get 2x plus 2. Could I keep going? I suppose I probably could. If you want to get a common denominator, in this case it would be, I could factor out a 2 even. Anyways, it would be this times this, and then you can simplify and get the numerator, but really, at this point, if you can get that far, you're good to go. Again, if it's a multiple choice question on the AP exam, you'd want to be able to recognize that if you do add these functions, that results, which I think is 3x plus 2, and I'll leave it up to you to get this. 3x plus 2 times 2x times the quantity x plus 1. You would need to recognize that these are equivalents to each other. But otherwise, this answer is just as good as that one. Alright, so what if we have something like this? The natural log of 1 over x to the 5th. Well, this says 2 ways, but we're actually going to do 3. I'm going to give you guys the bonus way to handle this problem. So way number 1 is I could just change this to the derivative of x to the, natural log. Don't lose your natural log. That would be all bad. The natural log of x to the negative 5th. Composite function, need the chain rule, we can do this. So what do we wind up with? We wind up with derivative of natural log is 1 over blah, so x to the negative 5th, times the derivative of that blah. So it would be negative 5x to the negative 6. So this is equal to negative 5x to the negative 6. You can either put it over x to the negative 5th, or since it's 1 over x to the negative 5th, this is really times x to the positive 5th. Any way you want to do it. So just give you negative 5, and then add the exponents. That would give you negative 5x to the first power, negative 1 power, sorry. And then that would be negative 5 over x. And that would be your answer. Alright. Way number 2, just looking at this a slightly different way, might be to use those log rules that we talked about in the last set of notes. And that might be to change this into the derivative of, this is a quotient because you have 1 over 5. 1 over x to the 5th. So you can change this to the natural log of 1 minus the natural log of x to the 5th. So that's using the quotient rule for logs. So, why might you want to do that? Well, when I go to find the derivative of the natural log of 1, the natural log of 1, this is just a constant, right? So what's the derivative of that? The derivative is just 0. So then we have minus, need to find the derivative of natural log of x to the 5th, so that would be 1 over x to the 5th times the derivative of x to the 5th, which is 5x to the 4th. So you're going to get 5x to the 4th over x to the 5th, and then that's going to simplify down to negative 5 over x. Haha, same answer both ways. Pretty fancy. Okay, so then you get the bonus way number 3, which I need to make some room for. Alright, here it is. So bonus way number 3. Oh, that's the ugliest way I've ever written my whole entire life. Alright, and here's what way number 3 would be. We have the natural log of 1 over x to the 5th. So what if I change this to the natural log of x to the negative 5th? But then think of it this way, using that power rule that says if you have the natural log of... got a little distracted there. Life happened. Okay, so if you have the natural log of x to the negative 5th, then I can change this to this negative 5 can be put out in the front, and that would be negative 5 times the natural log of x. Remember that little rule that says you take the exponent, you pop it out in front. So now, when I go to take the derivative of that, then we have the derivative of a constant. We can just put that out in front, and then just take the derivative of what's left, which is the natural log of x. That's just negative 5. And then the derivative of the natural log of x is 1 over x, so we get negative 5 over x. Same answer 3 different ways. If you ask me, this one's the easiest. Yay, calculus. So the next problem is just a regular log problem. So we have log base 3 of 7x, and we want to find the derivative of that. So two ways, again, to do this problem. First way is just to use rule number 2. That's what this says, but what the heck is rule number 2? Look at the top. It's just the derivative with respect to x of log base a of u is equal to 1 over u times the natural log of the base, so a, times, if you need, using chain rule, du dx. Alright, so just applying this rule, if we're trying to find the derivative with respect to x of log base 3, so a is 3, of 7x. 7x is a function, so that would be our u value. Then we're going to get 1 over u being 7x, times the natural log of the base a is 3, so it's natural log of 3, and then times the derivative of u with respect to x. The derivative of 7x with respect to x is just 7. So simplifying, the 7's would cancel each other out, and we're left with 1 over x times the natural log of 3. Alright, second way to do that problem, if you forget rule number 2, as long as you can remember that the natural log of x is 1 over x, and then of course use the chain rule if you need it, if it's not just an x, then doing it way number 2 might be a little bit easier. So if we begin by using the change of base formula, the log base 3 of 7x would be equal to the natural log of 7x over the natural log of 3. So if I go to find the derivative of that, d with respect to x, well, I can think of it this way. You have 1 over the natural log of 3. That's just a constant. And then I can separate that times the natural log of 7x. So what I just did is I took that fraction and I separated it into a product of a constant, 1 over the natural log of 3, and then times the function I'm actually trying to find the derivative of. So using the constant rule for differentiation, you can bring the constant out in front and then just take the derivative of the function itself. So we're going to be left with 1 over the natural log of 3, just your constant, and then the derivative of natural log of 7x is 1 over 7x times the derivative of 7x. That was chain rule right there. So the 7's are going to cancel each other out, and I'm left with 1 over x times the natural log of 3. So we got the same answer either way. Alright, so why don't you guys try to do the next one? It's really similar to the one that we just did. It's log base 6 of e to the x. Try doing it both ways. Press pause and then come back. Okay, so hopefully you're back. Way number 1 would be to apply rule number 2, which is sitting right up here. So if we go to find the derivative with respect to x of log base 6 of e to the x, then we're going to set that equal to 1 over u being e to the x, times the natural log of the base, so the natural log of 6, times the derivative of the u function, which is e to the x. We learned yesterday that the derivative of e to the x is e to the x. So now we can simplify. The e to the x's cancel each other out, and I'm left with 1 over the natural log of 6. Alright, way number 2 would be to rewrite it using the change of base formula. So let's try doing it that way. Log base 6 of e to the x. Using change of base is the natural log of e to the x over the natural log of 6. So that can be separated out into 1 over the natural log of 6, which again is just a constant, times the natural log of e to the x power. Of course, the natural log of e to the x power is just equal to x, right? This is, I already wrote, this is a constant, and then this natural log of e to the x is just x. So now what I'm trying to do is just to find the derivative of a constant times x. So if I do d dx, and all I have to do there is pull the constant out in front, so it's 1 over the natural log of 6, times what's the derivative of x with respect to x? It's just 1. So I'm left with 1 over the natural log of 6. So that way, I think, is even easier, because really all you're doing is taking the derivative of x. All right, let's do a proof. I know you're dying to see one. This is the proof of the property that we learned yesterday, that the derivative of a constant raised to the x power is equal to the natural log of that constant times the constant to the x power. So we're going to prove that this rule from yesterday, which is the derivative of an exponential function, that this rule is actually true. And we can do it now that we have the derivative of logs. So here's what we're going to do. We're going to begin by letting y, this new variable, be equal to what I'm trying to take the derivative of, which is a to the x power. All right, so the first thing that I'm going to do is I'm going to take the natural log of both sides. So we'll get the natural log of y is equal to the natural log of a to the x power. All right, so what I want to do is, actually before I do anything else, do you guys all see that I have an exponent? So I can use that little power rule that says that the natural log of a to the x is equal to x times the natural log of a. So that's going to come in handy when I go to take the derivative of both sides with respect to x. The derivative with respect to x of both sides. What's the derivative of natural log of y? It's 1 over y times the derivative of y with respect to x. And now when I come over here, I'm taking the derivative of x times, that's right, I said it in that annoying voice, but tricked ya, because the natural log of a, that's not another function, that's just a constant. So what that means is I can pull that constant out in front and then just times that by the derivative of x with respect to x, which of course is just 1. So it looks like dy dx is actually equal to the natural log of a times 1, so it's just the natural log of a. And then I want to make sure that I isolate the dy dx, so I'm going to multiply both sides by y. So it's y times the natural log of a. But I don't want a y inside my answer for the derivative, so dy dx is equal to y. What is y? Oh yeah, y is this right here. Y is just a to the x. So what I did is I substituted in for y. So I have a to the x times the natural log of a, which of course is my rule for finding the derivative of an exponential function. Woo, fancy. So I'm feeling like this was probably enough torture for one evening, and certainly enough to get you guys started on your homework assignment. So we're going to finish the rest of these notes tomorrow in class. So that'll give you a reason to keep living, a reason to wake up in the morning so that you can come to AP Calculus and finally finish the rest of these notes. All right, bye guys.